So my name is Frédéric Parienté, as Laura said, from NVIDIA, from the AI Technology Center, where we help AI researchers do their life's work on NVIDIA software and supercomputing systems at scale. My talk today will focus on the computing aspects of sustainable AI, the computing systems and considerations to have in mind to lower their energy consumption. Are the slides moving?
Yes, all is good. Yeah.
So why are we even talking about energy consumption in AI today? We are witnessing a dramatic increase in model growth, and with it, an increase in compute requirement. And this trend accelerated greatly with the introduction of transformers, as you can see here with the green line. So there is this fear that the data center energy consumption, which is roughly 2% of the world's consumption today, could explode as AI models continue to grow. Oops. Is the answer to stop innovating in the AI space? Likely not. Generative AI is advancing research across many domains. You can see here in chemistry, astronomy, healthcare, and so on, with tremendous benefits to mankind. It may even be possible that the gains to society from AI offsets its energy cost. When you're able to more precisely predict the weather and avoid catastrophes, you're saving on the energy and materials required to repair. Same goes with helping firefighters with wildfires and avoiding forests to burn. But in any case, whatever gains AI brings to mankind, it is not a reason not to do AI computing right. That is in the most sustainable way possible. My message today is that sustainable AI computing requires an accelerated computing platform. The word platform is actually of paramount importance here. Just an accelerator, just an ASIC or GPU is not the answer. Such a platform has three characteristics. So indeed, accelerated hardware at the bottom, that's the engine, but it also has depth. So, we're talking about full stack acceleration and also width acceleration across many workloads. And I will cover those 3 points now. The world's data centers are largely still equipped with CPU, and they are very inefficient at AI computing, at most forms of heavy computing, in fact. So the priority is for the world to migrate commodity clusters to GPU accelerated ones. What gains could we expect from this? In this example of image classification, you can reduce the chip count by 20x and the energy consumption by 13x. Both are important, right? The chip count, you need to produce the chips, and that also has energy impact. In this next example of recommender systems, you can reduce the chip count by 26x and energy consumption by 21x. In this other AI example of LLMs, you can reduce the chip count by 24x and energy consumption by 20x. So as you see in the AI space, just moving off commodity computing gets you on average a 20x improvement. Finally, even with pure HPC apps, gains are lower, but still you see a 5x decrease in chip count and energy consumption. It is, however, not enough that GPU do better than CPU. They also have to keep up with the growth in models, as we've seen. That is, we want the performance per watt of a GPU to increase by an order of magnitude, generation after generation, to handle larger models with only a moderate increase in data center size. And they do at NVIDIA. So generation after generation, NVIDIA has introduced innovation like the Tensor Core, like the Transformer engine to keep up. If we actually break down those gains over multiple generations, we see that they come primarily from the number representation. And AI gives us a lot of room to actually exploit that. Secondly, they come from the use of complex instructions. Next, from process improvement, and finally from sparsity. This slide is actually taken from a really interesting presentation from our chief scientist, Bill Daly, on trends in deep learning hardware that you can easily find on YouTube. In this talk, you will learn, for instance, a very interesting point about the energy efficiency of complex instructions. Complex instructions help drop instruction handling overhead, which is 30 picojoules for fetch and decode, by orders of magnitude. A single, and here I will take example in the health precision, with health precision, a single FMA costs 1.5 picojoule, so you have an overhead of 2000%. And as you increase the complexity of the instruction, going to dot product accumulate, to matrix multiply accumulate, and so on, you can drop down the overhead to 16%, in the 20% range. So at this point, even a GPU, which is still a general purpose chip, is as efficient as a dedicated accelerator. And NVIDIA is not stopping. Blackwell is introducing FP4 and a 5th generation NVLink that gives another huge bump in computational and energy efficiency. Something I don't have time to talk about today, but it plays an important role in sustainability computing as well. Blackwell introduces advanced RAS features, RAS as in reliability, availability, serviceability, a new RAS engine to identify early potential faults that may occur so you can minimize downtime. Obviously, there is a huge time and energy sink in having to restart a job because a node went down. Moving on to point number 2, so your AI application is sitting all the way on top of a deep technology stack. At the bottom, you have those efficient GPUs that are delivering incredible amounts of flops, raw flops, quite efficiently. The last thing you want is that all these flops go to waste because of a middleware that is not capable of exploiting them fully and efficiently. We are talking here about full stack integration and acceleration. Another term that people use is co-design. At the level of single GPU, a good and specific example of co-design is the transformer engine library to work in conjunction with the tensor cores in the H100 and B100 GPU from NVIDIA. So the dilemma is the following: the hardware can do FP8 and soon FP4. FP8 runs at 4 times the speed of a standard single precision that most AI codes use, but a Lambda developer will not switch to FP8 because an indiscriminate use of it could impact convergence and accuracy. With the transformer engine library, this is automated. So at each layer of the transformer model, the transformer engine analyzes the statistics of the output values produced by the tensor core with knowledge about what type of neural network layer coming next and what precision it requires. The transformer engine decide which target format to convert the tensor to before storing it to memory. FP8 has a more limited range of than other numerical formats, obviously. So to optimize the use of the available range, the transformer engine also dynamically scales the tensor data into the representable range using scaling factor computed from the tensor statistics. Therefore, every layer operates with exactly the range it requires and is accelerated in an optimal manner. Beyond a single GPU, the next step is to make multiple GPU working together. As we add more GPUs to tackle larger models, the communication problem gets worse, you can imagine. and per GPU throughput could drop dramatically. For a 1.8 trillion parameter mixture of expert model, communication could represent up to 60% of the time. So this is why NVIDIA embarked in the development of a fast communication fabric called NVLink some years ago. In the latest generation, which is the 5th generation in Blackwell, the NVLink includes 18 links per GPU, providing 1.8 terabyte per second total bandwidth. That's 800 gigabytes in each direction. And that's 14x the bandwidth of FCAI Gen 5 that you find, typically inside a standard server. So, and you can further scale the NVLink fabric outside the box using an NVLink switch that sustain 130 terabyte per second in one 72 GPU NVLink domain. So that means in such a domain, each GPU can communicate at its own peak performance of 1.8 terabyte per second. So the rack that you see here has all the hardware, the compute, but the communication fabric needed to become basically the new unit of compute for training very large models that require model parallelism. And again, we need the full stack acceleration. So you want the system to come with the full stack of libraries and software optimization. So none of that hardware potential is wasted. Under the Magnum IO umbrella name at NVIDIA, you will find the Nico library that implements the collective operation. And as you can see on the top right, we sustain close to 100% efficiency quite far in terms of number of GPU. And it also contains Sharp that does the in-network computing, something that was available in InfiniBand before, and now is made available for NVLink. But the full stack is much more than those libraries that I mentioned. So we need, and we have engineering working on all the layers so that your application that is running on top can run close to, quote unquote, the speed of light, that is the theoretical peak performance of the hardware. And in fact, today, although many people see NVIDIA as a hardware company, NVIDIA engineering is primarily software, more than 60% software engineering. The NVIDIA engineering also extends their efforts beyond NVIDIA software out to the community, because there is typically an extra layer between the AI application and the NVIDIA stack, typically a framework like PyTorch or more recently JAX. So for each popular framework, NVIDIA has a small group of engineers optimizing those frameworks, packaging them as a container for download from the NGC repo, etc. So in the end, your application can run at the speed of light, a condition for sustainable computing. I need to accelerate, I see Laura. An interesting data point to show how much software optimization actually counts in the overall performance. And it is very significant. The reason, again, why simply focusing on a hardware is insufficient. This graph compares in light green the performance of A100 and H100 when they were both first introduced. But in the 2 years in between, the software engineering improved by 2.5x the performance of the original A100 by simply improving the software. So that means that a third of the H100 performance boost actually comes from the software and full stack acceleration. So that's quite significant. And this is just a teaser. The ultimate delivery of full stack acceleration will take the form of microservices, something NVIDIA announced at GTC, and I'll just leave you with this information. You can look it up. You can look up names. Very quickly, my third and last point. So far, we've seen how we need accelerated computing with a software stack on top, co-designed to deliver the full acceleration to your application. I am not, however, going as far as saying that a highly specialized device is the solution. In fact, on the opposite, you still need a general purpose platform that can accelerate a variety of workloads. The rationale behind general purpose platform is that the research pipeline is not monolithic. Researchers run very different workloads, from data analytics to deep learning to simulation, and more is coming with quantum, for instance. So you need to acquire, if you needed to acquire many specialized systems and move data from one to the other, it would not be efficient, it would not be sustainable. So you still need a general purpose platform. And NVIDIA has managed to deliver such a highly optimized, specialized code path while keeping the platform very general purpose, thanks to the CUDA Foundation, where the U stands for unified. And after 20 years of taking CUDA acceleration from one domain to the next, NVIDIA has created this highly valuable platforms of science that has those three elements that I mentioned at the beginning: acceleration, depth, and width. And sustainable AI computing requires such a platform. I will end with a recommendation reading, just a call to action. So we recently, I mentioned, had our GTC conference. Check out this session for a more thorough analysis on the environmental impact of AI and how the industry is working at minimizing it. And with this, I will end my presentation, and thank you for your attention.